Good afternoon. My name is Mike Toole, and I have the honor of serving as the Dean of the College of Engineering here at the University of Toledo. It's my pleasure to welcome you all here today to a first in a series of seminars that the college will focus on autonomous vehicles. The series will touch on a set of technologies and systems that are clearly some of the most exciting innovations in our society today. So as a professional engineer, I find the product and process technologies and systems that are underlying the growth of autonomous vehicles to be awe-inspiring. I'm truly proud to be associated with a community of scientists, engineers, technologists who are pursuing inventions and innovations that have the potential to provide mobility to millions who would not otherwise have it, make our lives more efficient in terms of commuting time, reduce the carbon footprint associated with the movement of goods and people, and prevent tens of thousands of traffic deaths per year. However, I and others believe that the autonomous vehicles have the potential to be the most disruptive technological innovation of our generation. Disruptive to individual organizations, disruptive to entire industries, and disruptive to the social fabric that underlies our daily existence. Sociologists and other disciplines have written about the unintended consequences of technologies that on the surface appear to have only benefits. To help us anticipate and manage the potential unintended consequences of autonomous vehicles, we need to invite humanists and social scientists and others to join the conversation with engineers and scientists, industry and government leaders on how best to implement autonomous vehicles in our society. So providing a venue for this conversation and for the learning that needs to enable those conversations about autonomous vehicles is what this year-long bi-monthly series is all about. Today's seminar will be an overall education of the autonomous vehicles' possible contributions to society. It will also touch on topics that require deep thought from scholars, industry, and government. Future seminars in this series will drill deeper into the possible issues that can arise from inventions that bring about societal change, such as cybersecurity, changes in infrastructure, government regulations, and accessibility and mobility issues. So thank you for joining us here today. I'm very pleased to introduce our MC for today's event, Ms. Lisa Guyton from 13 ABC News. Lisa has been a television anchor and reporter for nearly 30 years. She spent the last 13 years working at 13 ABC. Lisa grew up in Perrysburg and graduated from Maumee Valley Country Day School. She has a degree in communications from Stevens College in Missouri and is grateful to be doing what she loves in her hometown. She's been covering the auto beat for more than a decade. Of course, there's a lot of recent coverages focused on self-driving vehicles. She also reports on many animal, business, and human interest stories for the station. She describes herself as fiercely loyal to our city, and she's proud to be involved with events like Technology Takes the Wheel. She volunteers her time for a number of charitable organizations in the community. A lot of her spare time is spent with Real Horsepower. She's an avid equestrian who began riding horses at the age of 4. She has a new horse that is actually showing up at one of the first competitions as we speak today. So thanks for being here today, and please join me in welcoming Lisa.
Well, thank you so much for inviting me to be part of this. As he mentioned, I've been covering the auto beat for more than a decade now, and it's been an absolutely fascinating assignment. I'm not sure how I came upon the assignment. One day I believe I did a story on Jeep or General Motors or Ford at the time. That's how long I've been doing this. Ford had a plant here in the area, and just ran with it and have been doing it ever since. And it really has been an incredible experience to see all of the changes in that industry, and of course Toledo's close connection to the auto industry. And we all know that we build those world famous Jeeps here. Who knows whether some of those will become driverless someday, but obviously our local workforce will be at the forefront of all of that. And so it's really been a wonderful experience for me to be able to share those stories of our city's rich connection to the industry, and then also to talk about some of these pieces as we move forward. I did a story not that long ago about the Ohio Turnpike and its testing of the driverless semis up on the toll road, and that was fascinating as well. I want to remind all of you today that any questions that you may have, write them down on those index cards that you have and hand them to the helpers who will be walking around the auditorium during the panel discussion later in the program. And please hold all of those questions until the panel discussion. Mr. John Nielsen of AAA was originally scheduled to speak here today. However, he was unavoidably detained, and Mr. Greg Brannon graciously offered to take his place for us this afternoon. Greg is the Director of Automotive Engineering and Industry Relations, Automotive Research, and Testing for AAA. He oversees automotive research and testing at AAA. His focus is building AAA's technical expertise on emerging automotive issues to serve the association's 56 million members. He is regularly featured as an expert on automotive technology in national media and has appeared in the Associated Press, USA Today, and Car and Driver. Leading AAA's automotive industry relations, Greg also has been a featured speaker at national safety conferences, fosters AAA's relationships with industry stakeholder groups, and provides guidance to the automotive and safety industries. Please join me in welcoming Greg Brannon.
Thank you very much, Lisa. I appreciate the introduction, and thank you for joining us today for this this exciting event. I'm very happy to talk with you today, and excited about the opportunity to participate in this first of this series on autonomous vehicles here at the university. So before I get started, just to understand my audience a little bit, how many engineers do we have or engineering students do we have in the audience by a show of hands? Oh my goodness. Okay, well, I think I'm in the right place. It's fantastic. Well, I'm the first to admit I'm not an engineer, but I've got some really great ones that work for me on the team. We do some really exciting work, and you may not think of AAA in that space, but we'll hopefully by the end of the presentation, you'll understand a little bit more about what we do and how we're working to help educate consumers. So today, I want to share with you a little bit about the levels of autonomy, as well as some of the projections for how we see the autonomous space playing out over the next few years, and some of the barriers that we may experience, like infrastructure and consumer acceptance of the technologies. As Lisa said, AAA is a 115-year-old organization, and we do this work really on the benefit, or on the for the benefit of our 58 million members, and we strive to understand the latest technologies that are available in vehicles and share the information with consumers and our members so they can understand the benefits and the limitations. And we've tested everything from the best fuel to put in your car up to the latest systems in autonomy, and we'll focus on the autonomous aspects today. In addition to that, we also do some consumer survey research that gives us an idea of what consumers are thinking about the technology and some of the things that we can do to overcome any of those obstacles. So today I hope to share with you some of those findings. So as engineers or engineering students, you've probably seen the SAE-defined levels of autonomy. These were supported by NHTSA and generally agreed in the automotive community at this point. So just by a show of hands, who's familiar with the levels of autonomy? And give me an idea of how deep we need to go. Okay, so a few. I'll give you a kind of a high-level overview. So whenever we talk about autonomy, and when we hear about it in media or we talk about it at a research level, it covers a wide variety of things. And the SAE definitions were the best attempt to try to put them into some boxes. An important note is even the engineers that were involved in the creation of these standards are quick to point out that the standards in many cases were developed well after the vehicles that you see that are on the road today, noting that most vehicles have a time from development through to the time that you might find them on the dealer floor of somewhere between 5 to 6 years. So the standards in some cases are really looking forward, and some of the technology that we have today, trying to fit them neatly into one of the boxes is a little bit more challenging. So the scale starts with zero, or implies zero or no automation, and I'll clarify a little bit more about what that means, all the way up to level 5 of full automation. And this is, again, there's a lot of steps and nuance between the levels, so we'll talk a little bit about that. So let's talk about no automation. So I'm a car nut. I've got about too many toys, and but I love all of them. One of them is my 58 VW, right? So it has absolutely nothing to assist me, right? I am doing every mechanical aspect of that thing. It doesn't have cable brakes, but it's got hydraulic brakes, thankfully. But I am driving that thing. That is not what level 0 means, right? Level 0 is talking about a level of automation that does not actively assist the driver. So it includes things like blind spot monitoring and rear cross traffic alert systems. So these systems don't take corrective action, but they may provide information that help the driver do a better job of driving or stay safer on the roads. So blind spot monitoring, for instance, uses radar technology to see if there's a vehicle in the blind spot, and depending on the way the system's calibrated, and Dave Hobbs from Delphi will be able to tell you a little bit more about calibration and how different that might be among manufacturers. But depending on the calibration of the system, it can see a vehicle very far back, or some of them, very close to the vehicle, depending on how the system is designed. AAA's tested these systems, and we've found that in general they have difficulty finding a fast approaching vehicle. So if you think about the very common situation, like I experienced getting on 275 here today as I was coming from Detroit, merging onto an entrance ramp, and you have a fast approaching vehicle coming, and you're accelerating on, the systems have a very difficult time finding that. And that's important to note as we build on these steps, that these are the systems that underlie full automation. In one of our tests, we also looked to see if these systems could find motorcycles, and we found that the systems missed them some 26% of the times during our testing. So it's important to note that these systems, I'm sure many of you have a vehicle with blind spot monitoring in it, that again, it's a building block towards autonomy. Far from perfect, but sure, a whole lot better than not looking over your shoulder, using your mirrors properly. It's an aid to driving. Another aid is the rear cross traffic and alert system, much less common than blind spot monitoring. We've done some testing on this system as well. And while they do a nice job of alerting you if backing out of a space, because we have as Americans just can't seem to find a way to back into a space. We're always pulled nose in and then have to back out into traffic. Seems like the rest of the world does that a little differently, but so these systems have been designed to help in that situation identify if there's a vehicle coming that you're going to be backing into. Ours has showed that the systems failed to detect a passing vehicle some 30% of the time. And a motorcycle was failed to detect some 48% of the time. And a bicycle, while not all the systems were designed to detect that, missed them some 40%. So again, a great aid to driving, but certainly not a replacement for backing out slowly, making sure that you are aware of your surroundings, and using the systems that you have here in your head, your eyeballs, as well as a critical part of the system. Okay, so we're moving up the scale to now level 1, where we think that, okay, we've gone from 0 to, okay, now the system is going to actively help me be a better driver, or aid in my driving. And so we've got a few examples that we can talk about today. And we're seeing these systems become more and more commonplace on vehicles, both as standard and optional equipment. Adaptive cruise control is one that's been out there for many years. In fact, well over a decade now. And has anyone, just by a show of hands, who's driven a vehicle with adaptive cruise control? Okay, good. So you have some experience with this, and obviously it's a different experience than normal cruise control where it will simply let you drive right into the vehicle in front of you. This system adjusts the speed to make sure that you maintain a distance between you and the vehicle in front of you, depending on how the setting that you have applied to the vehicle. What we found interesting is that the systems worked best when the distance between the vehicles was closer than that 3-second rule that we all kind of have grown up with and is in line with AAA safe driving policy. And that's because of the distance that it needs to get the proper radar reflectivity of the vehicle in front of it. So while the system's an aid to driving, it may actually in some cases bring you closer than would be normally safe to be following at highway speeds. Self-parking is another example of a level 1 technology, and we've tested these systems as well, and they work surprisingly well in the vehicles that the small number of vehicles that have them available. I believe Chrysler might have that system as well. What we found is that these systems did a much better job, particularly at parallel parking, than their human counterparts. And in fact, some 81% fewer curb strikes with self-parking systems than the humans that we compared them against. So a very good job. Again, a combination of sensors, both low-speed camera sensors, ultrasonic sensors that are testing things and maneuvering cars into spots that probably you or I would drive right past thinking, it's a little tight. The system can actually do a better job than the human in that case. Another example, and some of the engineers will argue where this specific technology should lie, if it's in level 0 or 1, but for our purposes, automatic emergency braking is a good example of a driver assistance system that is out there and will be standard on all or most cars by 2022. What's interesting about automatic emergency braking is that we found that that is a very broad term for a very specific technology that can be implemented in a variety of ways by manufacturers. Some taking the approach that some manufacturers taking a very conservative approach and saying that yes, we see that there's an object ahead. We're going to notify the driver that is coming through some type of warning, and then slow the vehicle down a bit before it makes impact. Now, keep in mind, you engineers in the room will know that there's a square involved in that, so the deceleration of any rate at that has a very large impact on the severity of the crash and reducing the severity of the crash. However, some systems do everything they can possible within the laws of physics to bring the vehicle to a stop. And there's trade-offs between the two, right? So if you're an automaker that you really are focused on safety and doing everything possible to ensure that your occupants are protected from an accident, you may take a more aggressive approach and again apply the brakes very hard, very early, and very aggressively. And I can tell you, as I race cars as one of my passions, and I can tell you that experiencing the automatic emergency braking in these vehicles is as severe as I've done on a road course, and it is surprising. If you take that technology and apply it towards a mass market vehicle, should that kind of event happen with a vehicle that someone's not expecting that to happen from, it may cause some consumer dissatisfaction with the technology, particularly in the case that it's stopping for, let's say, a steel plate that may be in the road instead of an actual vehicle. So that type of critical error comes at a balance. So automatic emergency braking, while it was fantastic that the automakers have come together and said that we believe this technology will save lives, the variance in the performance between the systems is dramatic, and that's something that the consumer is not going to know, and it is really not something that's safe to test out on public roads without period, not safe to test on public roads. So you are not going to know what type of system your car has until it's too late. So level 2 automation, just to be clear, level 2 automation is what's available in its most advanced forms for public purchase today. So this is Tesla's autopilot system, and this is Mercedes pilot or Volvo's pilot assist, and what's available on the new Mercedes, and there's a few other examples that are out there. This is where it brings the combination of both latitudinal and longitudinal control together and serves as an aid to the driver. So the vehicle does its best to keep you centered in the lane, as well as a safe distance between you and the vehicle in front of you. Some manufacturers extend that all the way to helping you in things like traffic jam assist. So just simply by maintaining your hands on the wheel, the vehicle may keep itself pretty well centered in the road and come to a stop and then reaccelerate should you be in a traffic jam on the interstate, for example. What's important to know about this technology is that it is not autonomous, right? This is still an aid to driving. This level of system that is available for purchase today is simply meant to make you a better driver, to keep you safer, and it is not meant to replace an engaged driver. And we're in the process of designing some test scenarios to better understand these systems, where they work really well as the limitations, so we can help inform consumers and be safe out on the roads when they're using the technology. So here's where it gets pretty interesting. Levels 3 through 5, and I've combined these because from an engineering standpoint, this is where that shift takes place. The driver is no longer the one that's responsible for operating the vehicle. So let's take it in a couple of bite-sized chunks. Level 3 is a scenario where the vehicle has control and is, let's say, driving down an interstate. That is the operational domain design that the manufacturers prescribed, that on an interstate you can engage level 3 and the vehicle will take control and is now driving you down the road, keeping you centered in the lane, keeping you a safe distance from the vehicle in front of you, perhaps even passing vehicles depending on your speed and your preferred speed setting. Up until it can't. So level 3 is a very interesting technology. So it's working well, things are going along, and all of a sudden there's a problem, right? Be that a problem from the roadway, construction, an accident, any number of scenarios, or even something like the angle of the sun. And it can no longer see the road markings on the interstate in a clear way through the camera system. And it says, guess what, driver? You're back in control. So you've just gone from reading your coursework on your iPad or your smartphone to, I need to re-engage in the task of driving. The interesting thing about that is some of the work that our AAA Foundation for Traffic Safety has done is that it takes some 20 to 30 seconds to move from a task like reading a book to re-engage in the task of driving. And the ability for a vehicle to see 30 seconds down the road when you're traveling at 70 miles an hour, well, you guys are better at math than I am, it needs to see a long way ahead that there's going to be a problem. So it is a very interesting technology. That's not to say that some automakers aren't going down this road. I believe Audi has announced that they'll introduce a level 3 vehicle this year, and I suspect there'll be others. And I really wish them good luck in that endeavor. It is going to be an interesting road ahead. So when we move to level 4, this is the level that we think about whenever the first image that pops to mind whenever we think of vehicle autonomy or a fully autonomous vehicle. A level 4 autonomous vehicle may not have a steering wheel or brakes in it at all. It may be a shuttle. It may be a vehicle that GM just recently is seeking an exclusion to put on the road without a steering wheel and brakes. It could be any number of things, but it's a vehicle that, in all likelihood, the driver or the rider in this case has no responsibility for its operation. The difference between level 4 and level 5 is that at level 4, the vehicle is designed to operate in a very specific scenario. So let's take the operation of, say, a shuttle around the campus here today. That shuttle could be driverless, and you may get on that shuttle and it will go from point A to point B to point C without anyone and the controls, and it using its own artificial intelligence to make that route. But it is driving a very prescribed route among campus. And the designers of that shuttle may decide when you get a snowfall like you had last night and this morning that the shuttle's not going to run today because we're not really exactly sure where the lane markings are. And so those are the kind of things that you need to take in mind or keep in mind when you're thinking about autonomy. Even at level 4, there's some restrictions around where and when those vehicles will operate. It's not till you get to level 5 where the commitment is that those vehicles are fully autonomous and can operate in any driving condition. That means that I could have, let's say 3 days ago, jumped in a level 5 vehicle in Florida, driven all the way up north through a couple of snowstorms and delivered it to the front door of the hall here today with no intervention from anyone, including myself as the rider. Not all that different than getting on the plane, except on the plane today, there was a pilot that was engaged, I hope, at some point in flying that plane. So that gives you a little bit of a background, and I apologize for those that are familiar with it, but that gives you a little bit of background on where we are today with the levels and our understanding of them. So it really brings us to the question of how long until hands off? How long until we'll be able to jump in a shuttle, ride to work with no one driving that shuttle? I always use the analogy of me summoning a vehicle to take my 12-year-old to school, right? So when are we going to get to the point when I'm able to summon a vehicle to my door? I am 100% comfortable with putting my daughter in that vehicle and sending her off to school and not giving it another thought. The reality is the technologies that will make up that self-driving vehicle or that fully autonomous vehicle are available today. And this vehicle, if you had a chance to ride in it, has many of these technologies like lane centering, adaptive cruise control, excuse me, and other things that really will underlie that technology. But it'll be some time before consumers have the opportunity to either buy or ride in a fully automated vehicle on their way to work every day. In fact, it may take decades, and we'll talk a little bit about the reasons why, including our somewhat crumbling infrastructure in the United States, a hodgepodge of regulations, and generally consumer acceptance of the technology. So let's start with infrastructure. According to, let's see, their own information, this would be the Department of Transportation, some 65% of the roads are in poor condition. And that is a troubling statistic. I think I may have driven on some of them in your bordering state on the way here. The reality is that things as simple as faded lane markings, or as you see, lane markings that have been worn away, bring the ability of the vehicle to sense the road that it's on to a halt. Because without simple things like lane markings or clear signage, we are really struggling the vehicle really struggles to identify its place in space. And while deep learning and 3D mapping and LiDAR and some of these other technologies that are on the horizon are going to help, they are not going to get us all the way there. Regulation. There's some 27 states right now that have regulations on the books related to vehicle autonomy. And as you may know, Ohio currently has a House Bill 608 relative to autonomous technology and looking towards the ability to test vehicles in the state of Ohio, and as well as reporting back any actions on a regular basis. So regulation is an important part of this because as you see, that's 27 states and most states have considered some other regulations, but we do not have a uniform set of guidelines for states or automakers to follow relative to autonomous testing. So some projections on when we'll get there. One estimate has by 2025, 1.1% of the vehicles on the U.S. roadways will be driverless. So 2025, a couple of years ago, did not seem, or it seemed like a long ways in the distance. But as we stand here in February of 2018, it seems to be coming very fast. For reference, 1.1% is about the number of electric vehicles that are on the road today. So if we think about the evolution of time that it's taken to build that infrastructure or that capacity, it is a long road to hoe. There's some 250 million plus vehicles on the road, with the average age increasing every year, and it takes time for a vehicle fleet to turn over. Another estimate, if we look all the way out to 2040, and I love these type of estimates because I'm not going to be around, and I'll hopefully be sailing away somewhere to say whether or not it was accurate, but another estimate has some 90% of the vehicles sold will be automated, and I think that's a pretty aggressive estimate whenever you consider the timeline between now and 2040. However, we will, the adoption and the increase, I think, that line is going to be very sharp as the technology comes on board and more consumers get comfortable with the idea. And really, that consumer acceptance is something that we are really focused on at AAA. We do an annual survey to keep a pulse on consumer acceptance of automated vehicles, and we've seen a decrease in the past year of people's fear related to autonomous vehicles. And now some 63% of U.S. drivers report that they would be afraid to ride in a self-driving vehicle. The good news is that's down from last year when they said it was when 78% have that fear. So we're seeing some easing of that fear, likely as a result of experience and exposure. So events like this today, experience with the technologies that underlie autonomy, bring people to a place where they feel more comfortable with the technology. Our survey has shown that people that have features like adaptive cruise control or lane centering are 75% more likely to trust the technology than those that do not. And as a result, it demonstrates that as these technologies become more widely available and more standard on vehicles, that we're going to see those fears ease and the adoption increase. The challenge is that driver assistance technology is often misunderstood. So going back to the earlier conversation, what we have today and what's available today is not an autonomous vehicle, not a fully autonomous vehicle. And there is a lot of opportunity for consumers and even us as researchers to get that wrong. And you see an example here. The role that we can play is one of education and really understanding what is available, it's the benefits of the technology as well as the limitations. You can see the driverless shuttle that AAA is involved with there in Las Vegas. That is an example of a level 4 technology. So we're doing a lot to try to educate consumers about the benefits as well as the limitations. There's a lot of stats and things that I've thrown at you today and kind of some realism about the technology in its current state, but I want to be clear that there's some 40,000 people that die every year on U.S. roadways, and that number's unfortunately been increasing the last few years. Automated technology has the potential to drastically reduce that because over 90% of those accidents are the result of human error. So we really do, as AAA, we really support the advancement of autonomous technology and its ability to reduce those number of fatalities on U.S. roadways. But we want to make sure that along the way, people are informed about the technologies, benefits as well as the limitations. And they hold great promise, and we're really excited. And as engineering students and engineers today, I think we're sitting in what I view as one of the most exciting times to be a part of the automotive industry. So thank you for your time today. Look forward to the panel conversation.
Learned a lot there. Thank you very much, Greg. And next in our lineup today is Mr. Dave Hobbs. He's the field service training instructor for Delphi Products and Service Solutions. Mr. Hobbs arrived here in Toledo last night in the vehicle you see right behind me here on stage. He spent a good amount of the day sharing his knowledge with the engineering students here at UT, as well as with all of the media. He was up bright and early with us this morning. Dave Hobbs' work at Delphi Products and Service Solutions includes developing training for the aftermarket with extensive OEM service and field engineering expertise. He has more than 30 years of experience in vehicle systems electronics troubleshooting, including 15 years in the independent aftermarket repair business. He is a master ASE L1 certified and has trained engineers and service technicians worldwide. Dave also teaches post-secondary vocational community college students as an adjunct instructor and is a regular contributor to several automotive service trade publications. Please join me in welcoming Dave Hobbs.
Well, who would think two little parts like this I could fit in the palm of my hand would revolutionize the world of automotive technology? But that's exactly what's going on today. When we get done with this, I want you to all come up as you want and check out this slightly damaged Chrysler 200 on its way in here this afternoon, and I'll show you where some of these parts fit, what they do, because I'm a hands-on nuts and bolts kind of guy. So let's go ahead and get started out a little bit about the maker of a lot of these parts. It's not really so much called Delphi anymore. If you look at some of those old logos from the General Motors components days, which really has its DNA rooted right here in Ohio, just down the highway a little bit in Dayton. The Delco Remy and Rochester products and some others like AC Sparkplug have merged together, and they were part of Delphi. Delphi was a spinoff from General Motors years ago, like 1999, when adaptive cruise control was kind of a new thing, maybe $3,000 or $4,000 option on a car. And so it definitely wasn't on a Chrysler 200, more like maybe a Lincoln or something. Also Packard Electric, which is Ohio, over in Youngstown and Warren area. And the Delco Electronics, my hometown of Kokomo, Indiana, the old Delco radio, they actually have merged together off of Delphi, the name, and they are Aptiv. So if you hear that term Aptiv, that's a company now. It's not a new company, it's the old Delco Electronics and Packard together, and the new company actually is the powertrain. So the folks that are getting you there with electrification, fuel injection, diesel, and so forth, and the controllers for propulsion are the Delphi Technologies, and that's who I'm with. And then Aptiv, the other colleagues that I have in Kokomo, they're doing the world of controlling and connecting the vehicle to get you there safely. And it all really kind of boils down to that guy right there. A show of hands, who recognizes who this is from engineering history? Who is that? That's Kettering. That's Charles Franklin Kettering. Who has been asked if you're cranky? You're kind of cranky today? Who's had that question asked? Every hand ought to go up, right? You know where that term came from? The electric starter replaced a bad day you might have had hand cranking your engine. So hand cranking like an old Model T, it could get a little bit hairy if you didn't have the spark timing set exactly right, which was done by hand, not with a microprocessor or even a mechanical set of centrifugal weights or a vacuum diaphragm, but by a lever on the steering column. And the air-fuel ratio, which was done years ago with a choke and now done electronically with air-fuel management, if you didn't get everything set right and you cranked the engine over, it could kick back at you and cause an injury. The guy named Henry Leland was the head of Cadillac Motor Division of General Motors in the early part of the 20th century, as in like 1905 or somewhere in that time frame. He had a friend that was hand cranking. That's where you get that term, cranky, because you had a bad time cranking your engine. Hand cranking a Cadillac, it kicked back, he had an injury, he had an infection and a complication and died of that injury. So Leland contacted this gentleman here who, speaking of hand cranking, electrified the cash register. from being the proverbial cha-ching. Who's heard of that? We've all heard of that. That means it's expensive, right? That's how cash registers worked. And then he electrified it. You pushed a button and it went cha-ching. He worked in his garage because he had a passion for the automobile as a hobby. Him and a couple of friends developed the first commercially successful and accepted 6-volt electric starter motor. And within a year, all Cadillacs had it as standard equipment, and it was optional and became a retrofit on Model Ts and cars going forward. That business that was developed by that gentleman right there was called the Dayton Electric Laboratory Company. What does that spell? Delco. That was the original part of Delphi. So that's our DNA. That's our history. And as we scroll forward, so we're pioneers of the past, propelling the present, and guiding the future. Now, it's not a commercial here. I'm going to tie this back in and try to inspire and rile some of you folks up if you're engineering students especially, or even if you're out there in the field and you're coming in here for continuing education credits, to get you some of that passion back, whatever you got back, whatever caused you to get into the industry to begin with. So as we move forward, let's look and see what ADAS is doing for the consumers here. Here's a little video clip. Oh, nice marketing commercial, all right? It's a neat system, and this is nothing like that, obviously, because this is a less expensive vehicle, but it does some of those things. Now, what the real challenge is going to be for us all is to help consumers that'll be buying the products you'll be building, whether it be something like this or some other area of industry, understand the technology in order to fully utilize it and not overuse it. If you want to see the opposite of something like this commercial, just Google Tesla ADAS abuse, and you will see countless selfies of idiots driving cars while they're in the passenger seat and there's nobody in the driver's seat, or while they're sleeping, playing cards, whatever. So where there is an excellence of engineering and ideas converging together to make great technology like Cadillac Super Cruise, there are going to be people that are going to not only not understand it and underuse it, but also overuse the technology. Now, I call this presentation ADAS for engineers in the rest of the world, because that's the rest of the world. They just want to know how it works and how it's going to affect me and benefit me. We want to know how it works to the nth degree, the nuts and bolts of it. So we just kind of look at this little animation talking about forward-looking long-range radar that's got a different frequency than medium range and so forth, and what it does, where the sensors are mounted. So we're going to talk about that when we get done with this presentations at 5. You can come up and look at some of the components. I'll show you where they are if you haven't already stopped by to see this. So 360 sensor fusion, LiDAR technology, so basically lasers instead of radar to determine distance and proximity and speed, and all the technologies working together. So let's take them one by one, the nuts and bolts of a car like this or the Cadillac with Super Cruise, and see how it all works together. So here we've got a picture of a vehicle that's got multiple radars, multiple frequencies, and multiple positions. The more sensor inputs, they call them sensor suites, that the vehicle has, the more accurate it can do, the higher level, as Greg talked about, the higher level of some degree of driver assistance or even autonomous driving. So backup aids have been around for a long time in the form of either ultrasonic, which I think is humorous. If you look at a Nissan service manual, it calls ultrasonic backup aids sonar. I'm thinking that has to do with like the Navy or something, right? Submarines and ships. It's sound nonetheless. So ultrasonic is sound we can hear that is beaming backwards. But some Fords actually have a combination, and have had for a decade or more, of ultrasonic. That's the little round little bumps you'll see, little cutouts in the bumper, painted the same color as a bumper, but it's about the size of a quarter. Those are ultrasonic sensors. They're very inexpensive, they're very simple, easy to test, and they help give you that beep, 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 beep as you get closer and closer and you back up, in addition to the cameras, of course, that we have today. By the way, those cameras have composite outputs, so they are a traditional camera like you'd hook up for a closed-circuit TV where you can look at with your lab scope and see the amplitude and frequency of the waveforms. Not so with the cameras we're going to talk about for the front of the car. But the backup aid may also, on some Ford models, the Park Aid module, they call it PAM, be supplemented with radar for more accuracy, one big radar unit. Blind spot monitors, that's radar. Side impact, of course, that's an accelerometer. But cross traffic for the rear and for the front, adaptive cruise control, as Greg talked about. These are a lot of different things going together with active safety systems to make the car more autonomous or more safer for you driving. So where do these things go? Here's cameras is the other world. So radar is part of that sensor suite. Cameras would be the rest, the other third of it, the third leg of the stool here. The cameras can be mounted in the grille, as you'll see cameras in the bottom of this grille. Also, you can have a radar in the grille. So they may have more than one camera. Here's a case where the camera is mounted in the windshield. If you see a windshield-mounted camera only, it may be a simple collision alert system or collision mitigation. So it's going to beep at you if your closure rate on the car that's either slowing down or you're accelerating onto is such a short time period that you're more likely to hit it than not, unless you apply emergency braking. So even if the car doesn't have emergency braking, at least it gives you a head up that you need to hit the brakes because you're about ready to have a collision. So those cameras are not composite output. They are smart cameras, typically on a CAN bus that's going to go into a centralized collision mitigation module. So we see multiple cameras on the active vehicle. This is a fleet of taxis in Las Vegas that's semi-autonomous. There's somebody babysitting the car, but otherwise the car is driving itself. And then cameras in the side view mirrors to help assist with the 360 or the bird's eye vision that you see on some cars where it looks like you're 10 feet above the car with a boom camera looking down over it to see more like where you are. That would have been kind of handy me pulling in here, I think, earlier today to have that 360 vision. So cameras everywhere, on the trunk, on the side mirrors, in the front, in the back, you name it. Also, to sometimes supplement or even replace the cameras is LiDAR. So a version of radar using lasers to do range detection and speed is being used in a lot of the Ubers and this is a prototype, I think, of the Google taxi. You'll see these things, I call them spinning trash cans on the roof of the car because this radar started out with a spinning antenna and now it's electronically scanned radar. LiDAR has moved into the grills of cars as well. So this is the Uber experimental fleet that's used in, I think, in New York City right now where there is a driver collecting data that's not really driving the car. The passenger really are kind of watching the automated car do its finest thing, but that's kind of ugly. I mean, Americans have a passion, love affair with cars. We're not going to put up with that. But as we see in future cars, like for example, the 2018 Audi has a very discreet-looking, small, not much bigger than one of these radar or smart cameras in the front bumper fascia of their cars hidden away, and it's doing the same job LiDAR has always done. LiDAR has been something that's been used in light aircraft that don't fly such high altitudes, because other companies that do mapping services for topographical mapping can actually use the LiDAR imaging. It's kind of a creepy looking image if you see it on like a camera, but nonetheless, it's a 3D image of what's out there, and they do topographical maps from small aircraft. So that's where LiDAR has been used, and now here it is shrunk down into a much more discrete package on this active automated BMW taxi in Vegas. And to top it off, we have other things. It's called sensor fusion, where we pull a lot of the hardware together. A lot of the hardware already has been there. If you think about your XM radio, you think about your GPS position antenna for navigation and so forth, those two antennas on one circuit board are going to pull together where you are with triangulation, typical GPS. But now the ADAS system is going to use them to determine, one thing they didn't say in the Super Cruise little video from Cadillac, was that they don't allow the system to work in an inappropriate area. If you think about getting out here on Douglas Avenue and trying to do cruise control, that's fine if you want to do that. Automated cruise control. This car did it all day long for the press drives that we took. But to do autonomous driving, hands-free, not a good idea. Would be better off if you did it out in the highway. So GPS tells the system where you are and doesn't allow you to do such advanced semi-autonomous features if you're in an inappropriate area. Also, steering angle sensor. Are you giving inputs? All the systems are looking for steering angle inputs. The challenge we'll have is making sure those sensors are robust, reliable, and inexpensive enough to be on every vehicle. They are today on every vehicle, because what system requires steering angle sensors? Who can tell me? Stability control, something that's been required by the Department of Transportation since 2012. So those are sensors. There's a blow up of a steering angle sensor, CAN bus, dual potentiometer, or optical type digital sensor. There are 3 or 4 designs out there, and they all work together for not only stability control, but now to be pulled into sensor fusion and used by ADS systems. The technology, let's say 5 layers of sensor fusion, pulling things together, your LiDAR, your radar, your long-range radar, short, medium, ultrasonic, whatever you have, pulling them all together, one convergence collision avoidance module, working on the CAN bus, and interacting with driver interaction such as haptic, where you make the seat buzz or the steering column vibrate, and also lights, of course, and sound to alert the driver when there's a problem. All working together. Also working together, a requirement for a car using emergency braking and autonomous or semi-autonomous driving, even adaptive cruise control, is some degree of brake-by-wire, where customers, or I should say consumers, sometimes are a little bit wary. They don't want the car steering themselves, but I got news for the average consumer or the average driver. They've been throttling themselves and braking themselves for years. And they're actually, to some degree, steering themselves now. If you've got one of those self-park features, you've got a degree of an autonomous vehicle. It can steer itself, at least in the parking lot. So brake-by-wire is something not new. If you've ever studied any hybrid vehicle technology, you know that to some degree you are asking the permission via a brake pedal sensor of a module to apply hydraulic brakes or not. In the case of regenerative braking on hybrids, you may actually be doing no hydraulic brakes on the front drive wheels, only some hydraulic braking, about 15% of the car's overall braking, by the rear wheels. So essentially, brake-by-wire has been out for, well, since the 2004 Prius for sure, and even before that. So to apply the brakes when your foot is on the gas or on nothing, you're just going along in semi-autonomous mode, you need a degree of brake-by-wire systems, which are also very complicated. This is a typical Generation 2 Prius, which I owned, and I lost my brakes completely because of a module that's not on any other car except a brake-by-wire vehicle, a module called a skid control module that cost wholesale $1,300. And that's not even a component you'd normally have on any regular car. That's a 2004 Prius. This is not a brand new car. that module went out. That would have been about a $4,000 repair retail at the average repair shop. So you can imagine some of the technology changes that are resulting in a lot of repair cost if education and onboard diagnostics are not exceeded to our expectations. If we slack behind as inventors and designers or as instructors and do not educate the people and the folks working on them, we're going to have a lot of problems with complexities like that. So also, using various things, I mentioned the haptive in the seats, the electric power steering, and the electric throttle. Throttle by wire has been about 15, 20 years so far now. You don't have a throttle cable we haven't had for years. So a lot of features that customers are a little bit wary of, they're already here. And there was the module I was speaking of that does the whole collision mitigation, or does, I should say, the anti-collision module, one that pulls all the sensors together with the sensor fusion, and they're located in various spots on different cars. So my little experience to wind out this afternoon was with a Volvo XC90, which did not have the full semi-autonomous mode. So it wouldn't drive and steer itself for hundreds of miles like some Volvos with the several $1,000 extra package, but it did have let's say a mile or so of steering by itself as it looked at the lanes, and it had the navigation, which knew where I was and told me to take a break when I didn't give sufficient steering wheel inputs for enough time where it says, I think we're having an issue with the driver not paying attention or being drowsy. It actually told me it's time to take a break, accept or reject. And I had to hit the button on the steering wheel control if I was going to have any more of that assisted power steering for a little bit of a degree of self-autonomous or self-driving feature. It did the brake and the gas by itself. I drove from Milwaukee, Wisconsin to northern Indiana, which is like a couple hundred miles, and I only applied the brake and the gas twice. If it hadn't been for a toll booth, an old-fashioned toll booth with a transceiver, but an old-fashioned arm that came down, I would have made it without the gas or brake except for just putting in gear and going. That was how good the features were on this car, and it wasn't full autonomous. The reason I had to use the gas and brake, the toll booth board, the arm, when it came down, the car couldn't see it and wanted to go right on through it. So that's why we still have to make sure the consumer, the drivers, the technicians, everybody understands how they work and how they don't work so we don't underdrive or overdrive the vehicles. There's the time for a brake alert that I got numerous times when I was just seeing what this system would and wouldn't do. So to finish up here, I want to give you a challenge. Where do you want to be? The past, the present, or the future? Who thinks they're in the future now? You're not. You're in the present, all right? We're not in the past. What we need to do is learn from the past. Learn from the not only the victories, but the mistakes. From Kettering right up through sticky gas pedals and bad ignition switches on General Motors and sticky gas pedals on Toyotas. Learn from those mistakes. Learn from the mistakes, let's say, of World War I aircraft engines from BMW had an issue with valves getting carbon on them. An engineer developed a process of using compressed air, like a sandblaster, to blow a media of a very forgiving, soft material, walnut shells, ground up walnut shells. If you've ever looked at Bass Pro Shops and places like that sell reloading supply for people who like to shoot and reload their ammunition, they polish the brass casings in a media of walnut shells, ground up walnut shells. That same media was blasted at the back of intake valves. They used that instead of silicon sand because obviously you don't want silicon sand in an engine, in a cylinder. So with the valves shut, they would clean this carbon off these valves that formed for whatever reason. In 1992, BMW and other manufacturers were having issues with non-gas direct injected engines with the same deposits. They developed for a different reason, and they were causing drivability issues. Guess what? An engineer at BMW remembered his grandfather who worked on, between World War I and World War II, German aircraft engines, and redeveloped, basically resurrected that old process. Now they put Techron, a chemical in gasoline that takes care of these deposits, And we didn't have any problems for about 20 years until gas direct injection came out and was not spraying fuel against the back of the intake valve. It was spraying it in the center of the cylinder. So there was nothing to clean the intake valves. Guess what came back? Carbon. Guess who remembered it again? An engineer who remembered their dad, who remembered the grandfather that found the solution to the problem. So thinking of things like an old guy like Kettering that died in 1950, whatever, that invented the electric starter, those things are relevant today to you in the present. So this is my third son, if you will, a friend of the family that I visit with every Monday. He comes to my house. He's an engineer at Delphi. I've known him since he was a kid in my youth group in church. And this kid grew up to be a fine young engineer that will take advice from the old man here about, hey, I'm not an engineer like you, Wesley. I don't do EMC. I know what it spells. I know it's electromagnetic compatibility, but here's what we learned in 92. Here's what we learned in 2012. Be open to learning from your elders, from your instructors, your professors, the people who have worked there in your company a little longer than you have, so that you can help the future. Now, here's the future. Now, this guy's an auto mechanic, or a technician, as I would call him. This fella is from Zimbabwe. I'm doing social media night before last, and I'm conversing with this dude in Zimbabwe instantly, and I'm thinking, I would never dream this when I was 20 years old. This would take a letter that would take 3 weeks for the post office to deliver, and I'm helping him with some information to help him take an ASE, Automotive Service Excellence, certification test so he can be the first person on the African continent who works on cars, who's certified to work on hybrid electric vehicles, the L3 Advanced Hybrid Test. And he was such a thankful young fella. He's the future. It's not just America, it's worldwide. It's the people who will drive the cars, use the products that you're designing, you're inventing, you're perfecting, and the people who will be servicing them. Because let's face it, to err is human. What happened on the way inside here with this car? All the technology didn't help it when the door hit the side of the back door, the overhead door here, and I dented a fender. People are going to do dumb stuff. People are going to make human errors, and parts are going to fail. Systems are going to fail, and these people are going to need your help. So I'm soliciting you as a fellow technical person, but as an instructor for automobile technicians. They're going to need systems they can understand, service manuals they can fathom, and test equipment that they can understand and diagnose what you build. So think about yourself in the present, because you are molding the future. Thank you very much.
Thank you, Dave. We are now going to watch a short video from a TEDx talk presented at a conference in Wilmington, Delaware in October of 2017. The presenter is Mr. David Silver, leader of the self-driving car program at Udacity.
Hello. I teach the Self-Driving Car Engineer Nanodegree program at Udacity, which is a 9-month program that trains software engineers to work on autonomous vehicles. Before I was ever a student at Udacity, or an employee at Udacity, I was actually a student. I was for many years a normal Silicon Valley web software engineer working in Ruby on Rails. And a few years ago, I got really excited about self-driving cars, but I didn't have any background in robotics or system software or automotive software, so I started taking classes online at Udacity and at other places to learn how to become an autonomous vehicle engineer. I was hired onto the autonomous vehicle team at Ford Motor Company at their Research and Innovation Center in Palo Alto, California. And later, the team at Udacity asked me to come and build out a program for people to do essentially what I had done, to learn to become autonomous vehicle engineers. At Udacity, we have our own self-driving car. Her name is Carla. And I'd like to tell you a little bit about how Carla works and how most self-driving cars work through the lens of some of the projects that our students have done as part of the Nanodegree program. So I think of self-driving cars as having 5 core components: computer vision, sensor fusion, localization, path planning, and control. Computer vision is how we use camera images to figure out what the world around us looks like. And sensor fusion is how we incorporate data from other sensors like lasers and radar to get a richer understanding of our environment. Once we've built this deep understanding of what the world around us is, we use localization to figure out precisely where we are in that world. And then once we figured out where we are in the world and what the world looks like, we use path planning to chart a course through the world to get us to where we'd like to go. And then the final step is control, which is how we actually turn the steering wheel and hit the throttle and hit the brake in order to execute the trajectory that we built during path planning. So these are the 5 core components of self-driving cars, and I'd like to investigate each of them with you. This is computer vision. This is a video that Carla took driving up Highway 280 in Silicon Valley. And this is work that one of our students, Vivek Yadav, did. Vivek is using computer vision, so looking for colors and edges and gradients to find the lane on the road. And then he's trained a deep neural network to draw bounding boxes around the other vehicles on the road. Deep neural networks, or deep learning, is an exciting new part of machine learning and artificial intelligence. And it's a way that computers can learn what cars and other objects look like simply by sending them lots and lots of data. They see lots of cars and they learn what cars look like. And you can see the deep neural network is trying to figure out, is that 1 car, is that 2 cars? And as they separate, it sees that it's a couple of cars. And this is pretty similar to what advanced driver assistance systems do on the road today. So once we know what the world looks like through camera images, the next step is to augment that understanding of the world using other sensors, so radar and lasers, to get measurements that are difficult for a camera alone to understand. So things like the distance between us and other cars and how fast other objects in the environment are moving. And what you see here is data from a trip that Carla took up El Camino Real, which is the main commercial street in Silicon Valley. And you see on the right the video feed of what that drive looks like. And the main image here is the laser scan of what the world around Carla looks like. And you can see this LiDAR, which is an array of lasers, doing a 360-degree scan of the world and seeing what the different objects in that environment look like and how they move. So once we understand both what the world looks like and how to measure it, and we incorporate those understandings together to get a rich picture of our surrounding environment, the next step is to localize ourselves in that environment. And you might think this is really straightforward because we all have cell phones today, they all have GPS in them, we all know where we are all of the time. But in fact, GPS is only accurate to within about 1 to 2 meters. And if you think about how big 1 to 2 meters is, if a car is wrong about where it is by 1 to 2 meters, it could be over here on the sidewalk hitting things. That would be really bad. So we have to use much more sophisticated mathematical algorithms as well as high-definition maps to localize our vehicle precisely in its environment to single-digit centimeter level accuracy. So this is work by one of our students. His name is Daniel Lopez Madrid. And what Daniel is doing is he is using a particle filter, which is a really sophisticated type of triangulation. And as his blue vehicle moves through the simulator, it's measuring its distance from various landmarks, and it's figuring out how far it is from these landmarks and where it sees the landmarks, and comparing that to the map, and using that to figure out precisely where it is in the world. And this is how self-driving cars localize. In the real world, those landmarks might be things like street lights, or traffic signs, or mailboxes, or even manhole covers. So once we've figured out where we are in the world and what the world around us looks like, the next step is to actually chart a path through that world to figure out how to get where we want to go. And this is path planning. Here you can see the work by one of our students, Kazuhiro Nakagawa. And what Kazuhiro has done is in our Udacity highway simulator, he's built a path planner that predicts where the other vehicles on the road are going to go, and then figures out what maneuver his vehicle should take in response. And then finally builds a series of waypoints. Those are those green pearls you see in the video for the car to drive through. That's the trajectory the car should follow. And you see when his vehicle comes up on other traffic, it has to figure out, should it slow down and stay in its lane, or should it shift right or shift left? And this is in fact the type of decision that real self-driving cars have to make all the time, subject to constraints like speed limits and acceleration limits so the ride is comfortable. And you can imagine this gets much more complicated in urban driving, where there are a lot more intersections and different maneuvers you can make, but in principle, the decisions are all the same. So once we've figured out what the path we want to take through this world is, and we know where we are in the world, and we know what the world looks like, the final step in the pipeline is control. And control is how we actually turn the steering wheel and hit the throttle and hit the brake in order to execute that trajectory that we built during path planning. So this is one of our students, Emmy Lau. This is Udacity's racetrack simulator, and she has a yellow line here. That's the ideal trajectory that her car should follow. And what you see is there's this green line layered on top of the yellow line, and the green line is the trajectory that her vehicle predicts it's going to follow based on the steering wheel and throttle and brake commands that it's sending. And what we'd love is for that green line to be 100% aligned with the yellow line, but of course that's really difficult. And as a human driver, you probably know this. It's really difficult, particularly on tight turns, to follow the exact line through the middle of the lane that you'd like to follow. But you do pretty well with it. You manage to drive, and in fact, computers are really, really good at this, and the distance between the trajectory they'd like to follow and the trajectory they actually follow is really, really close. So that's how self-driving cars work at a high level. We use computer vision and sensor fusion to get this rich picture of where we are in the world. We use localization to nail down precisely our location in that rich world. We use path planning to chart the course through the world to get us where we'd like to go, and we use control to turn the steering wheel and hit the throttle and hit the brake to execute that trajectory and ultimately move the vehicle. Everything else self-driving cars do are essentially more sophisticated implementations of these key functions, and this is how self-driving cars work. It is a really exciting time to work on self-driving cars. Computers are getting better and better at these tasks all of the time, and I hope you see self-driving cars on a road near you soon. My name is David Silver. I teach self-driving cars at Udacity. Thank you very much.
Well, we are now going to take a 5-minute break to set the stage for our panelists. At this time, please submit any questions you may have by holding up your card for one of our assistants, or you can bring it to the basket right up front here. We'll be back in a few minutes. Welcome back, everyone. I would like to introduce our panelists who are going to be part of the question and answer session of the program. Panelists today, in addition to Mr. Brennan and Mr. Hobbs, are made up of UT College of Engineering faculty whose research involves different aspects of the autonomous vehicle world. First, I would like to introduce Dr. Eddie Chu. He is a professor of civil and environmental engineering at the University of Toledo and the director of the Transportation Systems Research Lab. He has over 30 years of experience as a researcher in the transportation engineering field. His current research interests include transportation asset management, smart transportation systems, and applications of analytical tools, including multi-objective optimization, traffic simulation, and artificial intelligence to solve transportation problems. Dr. Chu has conducted more than $7 million worth of externally funded research as a principal investigator of more than 40 research projects at the University of Toledo. His research has been funded by the U.S. Department of Transportation, the Ohio Department of Transportation, and other transportation agencies. He and his students have published their work in top civil engineering journals, including the journals of the American Society of Civil Engineers and the Transportation Research Board. Dr. Chu's research is recognized both nationally and internationally. He received his doctoral degree from Texas A&M. He is a registered professional engineer in the state of Ohio. Also, Dr. Ahmad Javed is an assistant professor of UT's Department of Electrical Engineering and Computer Science and founding director of the Paul Hotmer Cybersecurity and Teaming Research, C-STAR Lab. He is an expert in cybersecurity, human-machine teams, and applications of data analytics. A1 and machine learning to cybersecurity. At UT, he has participated in research proposals that have led to a sum of $4.3 million worth of funding. These projects have been funded by various agencies, including the National Science Foundation, the Air Force Research Lab, and the state of Ohio. He played a critical role in the cultivation of a significant private gift to support the C-STAR Lab for cybersecurity research. And finally, Dr. Jared Olwash. He's an assistant professor of computer science and engineering technology at UT. He is program director of the CSET and IT programs, where he is responsible for advising curriculum review and ABET accreditation. He has received 2 NSF grants, the first of $50,000 for addressing information security with channel coding at the physical layer, and the second of $1.8 million for understanding how integrated computational thinking, engineering design, and mathematics can help students solve scientific and technical problems in career technical education. So we have a lot of brain power at this table. Our first question is, what key advances are still needed in autonomous vehicle technology before widespread adoption of this technology? That's probably a multi-layer answer, I'm sure.
I would say vehicle to infrastructure. That's going to be something that really needs to go quick if we want to see that become full autonomous.
And I would add that other than vehicle to infrastructure, there's also vehicle to vehicle communication. So the vehicle on board units and the IEEE 802.11p, which is the protocol that undergirds wireless communication, that needs to be fully adopted so that this technology takes shape.
Just want to chime in. Do you see traffic control interacting with autonomous vehicles?
Yeah, that definitely will be the case because vehicles relying on their own sensors and so on, we have seen a lot today, probably is not as efficient as the roadside units actually communicating those information to individual vehicles. So definitely the infrastructure, traffic control needs to be smarter because the stop sign and traffic light has been pretty much the same for the last 100 years. So we definitely need to see those things to be improved.
In the next 10 years, please talk about how autonomous features will impact vehicle cost.
There's no question that the technologies that we're talking about today add cost to vehicles, but I think Dave could attest to the cost and the size of the sensors are coming down dramatically. And as we see the technologies move from a $10,000 option on a high-end vehicle to something that's coming standard on a Honda Civic, you're going to see the cost continue to decline to the point where we see widespread adoption.
Is Europe significantly ahead of the United States when it comes to self-driving vehicles?
Yeah, so recently looked at several articles in the news and so on, and it seems that that is actually a fact. A lot of European countries are already doing, test runs and so on, and a lot of analysis and survey regarding, how it would impact real estate and, all those different markets, job scenarios and stuff. So I do believe that, yeah, Europe is I wouldn't say decades ahead, but like at least like a couple of years ahead of US in terms of like adoption of these technologies. But at the same time, as Dave and Dr. Chu also agreed that is still a lot of integration of technologies and infrastructure is still required there as well. Yeah.
Let me just add one thing. It's like I saw that Sweden has a proposal. Actually, they are already implemented that, including the infrastructure, vehicle, electrification of the vehicles, and so on, all together. So looking at solving the entire transportation problem as a whole. So they're not just driven by autonomous vehicle by individual companies. They're looking at a whole solution.
I think those are all pretty logical responses. I think to Europe has a higher population density in a lot of areas, so more pedestrian strikes, and the social conscious in Europe is a little higher over. Not to say that Americans, enjoy running over pedestrians, but the Europeans really dread it to the point where there's several models. Cadillac's one of them, where I've looked at the service manual and I've seen this optional European regular production option, they call it RPO, originally it was a front airbag for the outside of the windshield to protect a pedestrian's head from going through the windshield. That's the big thing about pedestrian strike, is the head injury on the windshield. You might survive the other bones that break when you go over the roof and then off the trunk and onto the ground, but the head through the windshield is pretty much fatal. So more recently, they went from the external airbag to a couple of pyrotechnic devices that work like an airbag, but on the back of the hood. So the hood actually on impact from pedestrian, and they can tell with the smart sensors if it's a pedestrian target. The hood then actually pops up at the back by the windshield, by the cowling, about 6 inches. And it makes the hood like I guess the best way to compare it to an old-fashioned locomotive with the cattle catcher, that little wedge thing on the front of the locomotive that make the cows kind of, push to the side instead of just smash them. That's what it does. It makes that pedestrian kind of wedge up over the windshield. I know it sounds bizarre, but go look at a Cadillac service manual and see for yourself. It is pretty insightful.
And speaking of, the American automakers versus the Europeans or the Japanese or anyone else for that matter, when I was covering the North American International Auto Show this year, there certainly is much more talk of partnerships. Sergio Marchioni spoke quite a bit about it. Chrysler has partnered with BMW. Are we going to see more of that? Is that unusual? Of course, partnerships between automakers is nothing new, but he talked about it quite extensively. And is that something that we'll see as we move forward with this technology? Do they have to do that?
Yeah, there's a lot of migration. I mean, we're seeing it with the engine on that Chrysler 200 has got technology right out of Fiat, which is their current partner. And we've seen a lot of technology from Daimler into Chrysler as well. So the connections between companies across the oceans and the migration of things from there to here and vice versa, it definitely does take place.
What we're seeing now is really a global phenomena, and you're seeing companies that you would never 10 years ago have thought that there may be an opportunity for partnership in areas like cybersecurity or deep learning. Whenever you're talking about an automobile 10 years ago, those weren't things that came to mind. And now you're having to work with, as an automobile manufacturer, you're having to integrate these systems in a way that addresses those issues. So you're going to have to bring in new partners to solve these problems. And that's a really key point. And really why this audience should be really proud about the work that you're doing here. There's a definite need for engineering expertise in Detroit today, in Toledo today. Toledo today. And the greater area.
Or maybe they need it more than we do. We have it already, right?
Right, exactly. Yeah, it's increasing every day.
This will be for you. What are AAA's thoughts on insuring autonomous vehicles as we move forward? Obviously, this is a very new.
Sure. So, insuring autonomous vehicles is an interesting question. Kind of go back to my presentation. The things that are available today, the systems that are available today, you still have the responsibility for driving that vehicle. So, the insurance that you're purchasing is still very much the traditional insurance model. I think as we look to the future, a fully autonomous car may not be owned by an individual. It may be owned by an organization, and therefore insured in a completely different manner.
This plays off a little bit of what you were talking about just a few moments ago. Is enough being done to protect pedestrians, cyclists, and motorcyclists?
As I mentioned in my presentation, some of the tests that we've done, I have to say right now the answer would be no. That pedestrians, motorcyclists, cyclists, all had greater levels of missed detections, in things like rear cross traffic and blind spot monitoring systems. The reality is they're smaller, they're harder to see, and they're very difficult to differentiate from background noise that the sensors are seeing. So the short answer is no. The more complicated answer is it's complicated and hard to make that differentiation. And I think automakers are working very hard to solve that problem.
It is. I can attest to that. I've had many discussions with Delphi and now Aptiv engineers, and actually seen them physically walk out in front of each other. One time I was picking up an engineering car, and I see this guy. I knew him, and I go, "He's stepping out in front of that guy in the parking lot. He's coming right at him." And I went, "Oh, they're testing." I mean, so it was really kind of like, I wouldn't say they're risking their lives per se, like, that dramatic, but it was, I thought, a little risky. So they're actually using themselves sometimes to step out and make sure the system is on the ball and can stop. Of course, there's a driver in the car ready on the brake. But I spoke to another engineer on motorcycles, and there's an interesting algorithm they run that's unique to motorcycles for blind spot detection, where when something the size of a motorcycle comes into the blind spot, they are making sure with the timing that the item either leaves and falls back. In other words, the motorcycle didn't pass you on that 4-lane, they actually slowed down or you speeded up, or they left the blind spot and went beyond you. If they don't see the movement, they keep motorcycles, or the smaller targets that they call motorcycles. They differentiate it deliberately from cars so that they make sure that the motorcycle doesn't slip through the software that's making sure that little light on the mirror is coming on and telling you there's somebody in the blind spot. Don't change lanes, because that can result in a fatality if you're out in the interstate and you change lanes and there's a bike right next to you.
Up next, interesting question. How will this technology potentially affect the agriculture business? Tractors, of course, have implements attached to them with no sensors. The new tractors by themselves can be operated as autonomous vehicles. But how would this technology be applied when self-driving vehicle is driving with an oversized trailer like a plow or a planter?
Yeah, so regarding that, I think it's already affecting these areas. Actually, I have a couple of friends who work in industry. Actually, one of my close friends is in Columbus working for a company who which designs these autonomous tractors, and they basically work with all these automated technologies, GPS and stuff. It tries to basically spray the pesticides and whatever you want to do actually in an agriculture field. So in a way, it's already affecting specifically the agriculture area, because it's a very different scenario from a vehicle driving on the street. I mean, it doesn't have to detect someone riding a bicycle or someone standing or walking pedestrians. So in agriculture field, usually you'll expect the whole field to be empty, basically, right? So basically it's already affecting that area.
How will autonomous vehicle technology impact other traditional elements of automotive vehicle design? How will autonomous vehicle technology impact other traditional elements of automotive vehicle design?
Greg, I'm sure you got an answer as well on aftermarket parts, because AAA has looked into that as well. But the body, the paint, aftermarket windshields, varying from anything that's not factory is buyer beware. As certain colors, black seems to be the most challenging color to make sure you've got a black paint that doesn't absorb the radar through the bumper fascia, as opposed to letting it go through and do its job. And then windshields with the least bit of like an aftermarket Chinese knockoff windshield versus an OE, Corning or whatever windshield. The least little bit of deflection or distortion can you see just fine through it. You do. But the camera doesn't. So those are some issues and any aftermarket accessories added, like grill protectors and things like that, and custom grills. Actually, we had an issue with a Cadillac CTS, or an older Cadillac years and years ago, with the big older adaptive radar unit. It made noise for one thing because it didn't do electronic scan. It physically moved internally, but it also would only work with a certain kind of grill. And the CTS owners preferred this European-looking grill that didn't allow the signal to go through. So the irony was, this expensive, back years ago, $3,000 option for an automated cruise control would only work on the lower level CTS, not the CTS-V or whatever, with the cool grill. And so it resulted in very low sales for us.
Will autonomous vehicles have the ability to talk to each other? Will they be able to coordinate with other vehicles near them in traffic? We have several questions along that line.
Yeah, they definitely have to. I mean, if you're thinking about traffic actually going on highway, and then we're expecting to hit a jam like maybe an hour later, so all the vehicles which are driving on the street should be well aware of that beforehand. And I think Greg, you were mentioning in your presentation that to plan ahead like 20-30 seconds, when we are driving on highway, that's actually a huge challenge, and that can be only accomplished when each vehicle is actually talking to all the nearby vehicles.
Yeah, and I might add that the U.S. Federal Communication Commission is actually responsible for assigning the wavelengths for that. So there's actually a protocol that has been built. And I think the question that then arises is, if you have multiple vehicles within a communication network and they're all sending information to each other, how then do you know for sure that this signal that you get from that vehicle is not a malicious signal from a hacker somewhere? And so there's a lot of questions going on, a lot of research going on into ensuring that, because the weak spot are actually the Wi-Fi spots, the Bluetooth spots that these vehicles are going to use to communicate. There's going to be a lot of encryption, public key cryptography. But even with public key cryptography, we now know that they're not 100% foolproof. So other new research areas into physical layer security, exploiting channel cores, the zeros and ones, and the physical layer, exploiting the channel state information, are coming into play, and I think this is a hot research topic even for graduate students.
I'd like to add one more thing actually in the same area, that whenever we actually design a system, we like to have actually redundancies to do the same task. So similarly, when we want to actually talk to other vehicles, then we just don't want to rely on cameras and stuff to basically look at the vehicle, because I'm pretty sure many of you must have read in the news that Google's deep learning based image detection technology was fooled by just a couple of pixels were changed in an image, and then a cat image was basically being detected as a banana or something. So so you don't want people installing certain design or a certain vinyl on their car, which makes other cars detect it as a, I don't know, maybe a deer or something, or maybe just a stone on the street, something like that. So, so we do want to have this intra-vehicular communication as well, to make sure that vehicles are talking to each other.
Yeah, the autonomous vehicle would probably be just the first step, because eventually it has to be connected. Because right now we're still relying on the line of sight, the camera, the lasers, and so on. You need to be able to see the object. A lot of time the crashes is like, what if there's a passenger step behind a bus, so you cannot see through, and he all of a sudden step up, and that causes a fatal crash. So that will be the kind of connected vehicle definitely has to be there to address all the safety and efficiency issues. If I can go back to the previous question about the autonomous vehicle affecting the traditional vehicle design, because think of how much we automakers put into the crash zones, put into airbags and all these safety devices. If the car won't collide, we can save a lot of money on those aspects and put those into, for me as a transportation engineer, we could make a better brake to make the braking distance shorter, because car manufacturers are always trying to balance the cost and so on. So if they put so much money into the safety aspects, well, for the car to be affordable, they cannot put their effort into where that can really improve the safety, which is the better brakes and so on.
What impact will this technology have on jobs, specifically for commercial drivers? And that, of course, was a big focus of the piece I did on the Turnpike with the commercial drivers.
As a computer scientist, I think of it as creating more jobs for programmers, for machine learning experts. I think commercial drivers might have to go back to school and learn some programming to make our world even a much better world.
Yeah, I was just having this similar conversation in the morning with Bob from AAA, and I was just mentioning exactly the same thing, that although it's predicted to actually eliminate a lot of jobs, but at the same time, this would be creating jobs, and especially for a company like AAA, maybe you guys would need to hire more engineers, because now you need actually people who can maybe check the programming, if the code is right or not, if the hardware is correct or not, and so on. Traditional mechanics may not be able to solve, basically repair those cars anymore, right? So So yeah, I mean, we hope for the best that it will create probably more jobs.
And of course, a lot of the mechanics today would tell you they're software engineers now.
Well, also it might affect the hours that you work in the service industry. If you service and do routine maintenance on vehicles, think about your home computer. When do you have the hard drive defragged or the hard drive ran for viruses? What time of the day? Middle of the night, right? 3 in the morning. Why would you want to be inconvenienced with an autonomous car by having to drop it off at the repair shop for an oil change and tire rotation at 8 o'clock in the morning on your way to work when you can have the car drive itself at 2 or 3 in the morning to the repair shop, have its oil changed, and its tire rotated by the technicians? So I can foresee a day where it'll be a midnight shift for a AAA approved garage where the car will pull up and I guess honk its own horn based on a smartphone appointment you made for a lube oil filter.
I think the job changes will not occur very quickly, just like Greg mentioned. It will take a long time. So I think the driver assist technology will be deployed quickly in the next few years. I think the automakers has been testing it, but the truly autonomous vehicle, they still did not put it on the market because the small issues like pedestrians or they don't want to have any of those happen. So they want to make 100% sure. So that would take quite a bit of time to make sure that doesn't happen. So human drivers still would be required. It's just maybe make the job a lot easier. You don't have to be on the wheel 8 hours a day or something, because eventually the technology will make the society so that perhaps most of us can work fewer hours than we are. Just like compare with 19th century, 18th century, those people work much longer time than we are now.
You could argue technology hasn't actually got us to that point yet. You do bring up a very interesting point, though. The technology in what we're talking about today in these driver assistance technologies, it is definitely going to be a long road. We talked, just briefly about vehicle-to-vehicle communications. Right now, there's no standardization around how that might happen. You have a few automakers that are experimenting with that. Vehicle-to-infrastructure, we haven't quite figured out how to fund, if anybody's noticed, infrastructure improvements. So these things, they're absolutely necessary to deployment. But the reality of making them happen today, we're just not there.
And just like in continuation of that, I just got this idea that since we need to do so much modification in infrastructure, and then a lot of infrastructure maintenance is going to be required, because you want to make sure that the lines on the highway are always visible, right? And it needs regular maintenance. So that would create probably more jobs. And then all the street lights in the whole U.S. actually would need to be, basically replaced. I mean, I don't expect any technology just to be attached. I mean, even if we are just attaching something, then we need actually people to do that job, right? So at least in the near term, we need probably more people actually working in those domains, and maintenance is actually going to create a lot of jobs as well, because we don't have yet robots which can do that work for us. So.
Are there infrastructure preparations that local governments can or should be making to prepare for autonomous vehicles?
Yeah, in terms of the technology part of it, I would say yes, because if you're going to have vehicle-to-vehicle and vehicle-to-infrastructure communication, then the wireless networks have to be put in place along the roads. But I think even the design of the road networks themselves have to be looked into, I believe.
Most of the roadway designs these days are still based on not that far from 100 years ago, because we're based on human driver assumptions. So we need 2 or 3 seconds reaction time and so on. So a lot of design code and design spec will have to be modified. So we move down this road. And I also think the infrastructure renewal has to be somewhat tied to this autonomous vehicle deployment, because the technologies, for example, you want to make the signal smarter, the signs needs to be smarter, so the vehicle can be able to see them easily and so on.
Will LiDAR transmissions from multiple cars interfere with one another?
That's an excellent question. What we do know about LiDAR today is that it is an evolving field, right? And if you've seen autonomous vehicles on the road, you've seen large LiDAR units that are placed on the top of the vehicles. This is scientific grade LiDAR. But converting that to something this size that's reasonable for automotive use is a large challenge. And again, I think it brings back the point that sensor fusion and fusion with the vehicle-to-vehicle and vehicle-to-infrastructure is absolutely necessary. You cannot rely on just that one signal to make a decision that's a decision of life or death, perhaps, of the occupants.
How will autonomous vehicles behave in a traffic stream with traditional cars or mixed vehicles around? And that's a good question because obviously it'll be a gradual process.
Some of the early work you can find there's been some studies that even just one vehicle in a stream of vehicles with adaptive cruise control can help the smoothing effect of the accordion nature of traffic. So the AVs in the traffic stream will improve the flow, there is no doubt. They also don't do this whenever they go by an accident, which I think we all know will improve traffic flow dramatically.
And we're doing some simulations at UT about the traffic flow when we put in some autonomous vehicle or connected vehicle into the traffic stream to see. People already show that very small percentage of connected vehicle is going to cause the traffic to improve. So we hope that that will pick up very quickly once become 5 or 10% in the traffic flow.
I'm reading someone's question. This is not me saying this. I may or may not agree with it. I enjoy driving and will never give up my car. How will autonomous vehicles affect me?
They may not in your lifetime, because this is my view is that everybody that's sitting in here today probably will always have the choice to drive a vehicle. Maybe not in every city and every location, but you will always have that choice. It's just the realities of the vehicle park that's out there today. It's going to be a mixed fleet for a very, very long time. So if you feel that passionate, and I'm an avid car lover myself, I think you'll have that choice.
Yeah, and I think that question actually, very much applies to me. I would probably not want to give up my right of driving, actually. And I completely agree with Greg that it's not, considering the level of technology and, how mature all of these technologies are, how compact these are, how, cost and all those things. I personally also believe that it's we are not going to get to a level 4 or 5, at least in next 20, 30 years. And I have no idea how GM is actually saying that in 2019 they'll start, marketing cars, selling cars which will have no steering wheels and so on. So we'll probably cross that bridge when we get there. But I believe that yes, at least for next couple of decades, people will have at least shared control. And if you wanted to let it drive by itself, it should. Or if you want to drive yourself, then again it comes back to the responsibility, right? When we were talking about insurance, the liability actually is of the driver, right? But when you just let it drive autonomously, then it's probably on the car manufacturing company and or whoever developed the software or whoever so all kinds of issues are there.
I think the people adapt to technology if they see the benefit very quickly, just like some of us older folks, we never had cell phone or smartphone 10 years ago. So it's like almost everybody has one in their pocket now. So thinking of this autonomous vehicle technology is the artificial intelligence has improved dramatically in the last 10 years or so. So that makes it possible to have these technologies. So if you realize your neighbors or your friends, they have this vehicle that they can feel very safe going out. It will not cause any crash. That makes a big incentive, right? And also related things, it's safe, it's relatively convenient, you can save that 1 hour of your time that on average people on the road drive on a daily basis. We all can have that 1 extra hour for doing whatever you like to do. So that would make the adoption of technology have a very steep curve.
Yeah, and that kind of agrees with the data also, which I don't know if it was your presentation or yours. Yeah, it was yours. Yeah, that the 78% actually reduced to 63%, right? In terms of how many people are actually willing to adopt, these technologies. So, so yeah, I agree, with you also that as we see the benefits and so on, I think yeah, it would maybe I would be ready to give up my driving someday. I don't know.
Well, a lot of people in this room, have grown up with computers, but being in the television business for 30 years, when I started, we were on typewriters. That wasn't that long ago. And I worked with gentlemen who did not want to give up their manual typewriter for even the electric versions. And I often think of the poor man who had to come in and train our newsroom to switch to computers. He probably quit right after that. But it's a way of life, and I laugh. The young people in the newsroom will say, well, how did you ever survive? Well, so maybe that's what we're going to be saying about the cars as well. We'll get used to it. This is a good question. They're specific with it, but I think it could be, applied to all of these level of vehicles. What kind of life expectancy does a level 5 car have? That's a good question.
That is an excellent question. And if you think about the use case for a level 4 or level 5 vehicle, it's probably very different than the use case for well, maybe I'm a bad example, but for one of my cars, to sit still for 95% of the time and only be used 5%. I think we're going to see that. I don't think it'll shift to 95% utilization, but it will certainly increase. So the life expectancy of the vehicles will likely go down as a result of that if we're talking about number of years. But if we're talking about vehicles mile traveled, I think electric technology holds a promise to extend the life expectancy in vehicle mile traveled for a vehicle just because of the reduced number of parts. So those things kind of counterbalance each other to some extent, but I think if we're talking about the number of years that a vehicle will be on the road, my best guess is that it will be less.
I think there's going to be a mix because, we mentioned the urban areas and level 5 where it's no private ownership, you're just a ride share, or actually it's almost like summoning the robotic taxi to come and get you. That is a good fit in like New York City, where when I've been there, I actually dread when I don't do mass transportation. If I have to, for a training reason, bring a specific vehicle in for hands-on training, it's this horrible game of finding a parking place in Brooklyn. And with the rideshare level 5 autonomous, where there's not even a driver, where you just basically summons the Uber that's driverless, that makes more sense for that area. But for other areas of the country, it makes no sense. And I think really, because of Americans' passion for the automobile, there'll be a blend. Like in Denmark or someplace like that, where there's a lot more congestion and a lot more social conscious for pedestrian strikes and not so much the love affair with the automobile, I think there'll be full autonomous a lot more. But here in the United States, we're going to see that mix, and it's going to be a nice blend. Because we're Americans, we'll make it work, and we'll like it. But there'll still be those street rods out there that'll make those great sounds that we like, and there'll still be those privately owned minivans that'll take us across the country. And for the folks who live in New York City, thank God there's going to be those driverless Ubers that'll pick us up and eliminate some of those traffic jams.
And just one quick question off this that plays well into that. How will self-driving cars affect ownership in the future? Because you may see people.
Yeah, so again, several conversations have been happening since morning regarding this topic as well. That since we always try to be most efficient, in everything we do, and the same concept is being applied to smart cars as well. That we, as just Greg mentioned, that the companies are targeting for 95%, efficiency, and then it's always moving. It's never parked or unused and so on, just to make sure that it's it's efficient. So in that particular model, companies are also targeting a model where there will be shared ownership. So as an example, if you are, in New York and your self-driving car is dropping you to work, what does it do? I mean, if it goes and park, then it's basically occupying a space and just being underutilized. So maybe there is a co-owner who is probably just shifting, ending his work time and stuff, and the car actually, he also co-owns it, and then the car actually drops him back at his place, and so on. So, I expect, and then I think a lot of experts would agree that there is going to be a shared ownership model with a lot of autonomous cars, especially in the bigger cities. But basically continuing on your answer of the last question, that in smaller towns and stuff, maybe we really cannot have that model. So then there will be basically independent ownership of vehicles.
A lot of fabulous questions here, and I apologize that we didn't have time to get to all of them, but maybe you can speak with some of them afterwards. And I want to give a heartfelt thank you to our speakers and panelists, some of whom have been here since 4:30 this morning, handling the press. That's, a tough job. And events for the students here at the College of Engineering. Thank you also to the co-sponsors of the series, the University of Toledo College of Engineering and AAA of Northwest Ohio. It's apparent that this series can help us ensure that Northwest Ohio is ready for the changes that are coming our way, and to make sure that we are leading the way in innovation and preparation. So please mark on your calendars that the next seminar in the series is going to be April 13th. Topic will be cybersecurity and autonomous vehicles. Also like to take a quick moment to thank some of the people behind the scenes for this. It takes an awful lot of work to make this happen. It runs, seamlessly, and everything came together well. But there's a lot of work that goes into making all that happen, and so I'd like to thank Patty and Diana. If you can both stand up quickly, I think we should give them a round of applause for what they do. Thank you. And for those of you who would like to attend the free reception, please exit through the stage left doorway. If you're unable to stay, exit stage right. And those of you who registered for CPD certificates, please pick those up in the auditorium lobby. That is stage right as well, right after this, and then you can make your way to the reception. Thank you, everyone, for attending this afternoon. Worthwhile discussions.